Hello, welcome to this little summary lesson on infrared spectroscopy, which is used to identify functional groups and usually goes in a package of other techniques to identify whole molecules. So here on the right we have a guy, a scientist, using an infrared spectrometer, and down here is where he's going to put this sample, and what the machine does is it shines all wavelengths of infrared radiation through the sample. And depending on the bonds in the molecules of the sample, the bonds will absorb certain wavelengths of infrared radiation, right? And so the machine also detects which wavelengths have been transmitted and which ones have been absorbed. Okay, so then it presents that information in a spectrum such as this, right? So you've got transmission as the y-axis here, right? And so certain bonds have absorbed a lot of radiation at about 2,700 cm to the -1, for example, right? And this pattern of transmission or absorption, one's the inverse of the other, allows you to identify functional groups, and that's what this little lesson is about. So as we've said, it's the bonds that absorb the infrared waves, and the machine that measures the wavelength of the infrared that's being absorbed. So let's have a look at this table. It's not unlike the table that you'll get in your data sheet that you can use in your exam. So here in this column we've got lots of different bonds. And here we've got the wave number range. Okay, so let me show you a spectrum. All right, and so notice that we've got the wave number is the x-axis, which corresponds to this column, this first column here. All right, and it goes from right to left, strangely enough. Just notice that. And then depending on what bonds are in the molecule, you'll get different absorptions. Okay, so let's just delve into this table a little bit more and look first at these bonds here. All right, so these bonds here all have an absorption at wave number less than 1500. Okay, so this is less than 1500, which corresponds to, let me change color here. Corresponds to about this part of the spectrum here. All right, so all of those bonds are in this region, which is called the fingerprint region. Fingerprint region. All right, and as you can see, it gets pretty hectic, and it's very difficult to read because you've got lots of different bonds, all absorbing very similar radiations. So usually we leave it to a computer to look at that fingerprint region. They can do it much more precisely, accurately than we can by eyeballing it, right? So in exam questions you're not generally required to read any data from the fingerprint region. So we're more concerned in exam questions with this part of the spectrum here, 1500 and above. Okay, so that's all these bonds, right? That's all these bonds. So exam questions tend to focus on aldehydes, ketones, carboxylic acids, right, and alcohols. Okay, so they're the four main functional groups that are in exam questions, because it's quite clear, esters not impossible, alkenes not impossible, and they are lots of the functional groups that we study. Okay, so let's look at functional groups one by one and see what their spectra look like. Okay, so we have the infrared spectrum of an alcohol here, and what we're going to do is learn the two things that allow you to determine that this is in fact the spectrum of an alcohol. So firstly, let's get up our table. All right, here we have our table, and that's the data that you have in the exam, right? And so let's connect the table to the spectrum. All right. So first of all, we've got let's use a blue pen. First of all, we've got this whole peak here, all right, which occurs. Let's look at it here. Occurs about 3,000. 300 or 400, yeah, and it's quite broad. It's got a characteristic broadness about it compared to some of the other spiky ones. All right, so we look at our table here, and we see that it's in this one here. So let's just make a connection between that and this. All right, you see that the wave number is in the range 3.2 to 3.6, right, clearly, and it's quite broad, right? And so that suggests it's the OH group, or the oxygen-hydrogen bond in a hydroxyl group of an alcohol. All right, we're going to distinguish between the alcohol and the carboxylic hydroxyl groups in a second when we look at the carboxylic acid. But here we've made a connection there. So let's also have a look at this little peak here. All right, so this little peak is about 2,900. If we sort of follow it down, it's about 2,900. So if we look along the chart, we've got 2,900 here, all right, and that's the carbon-hydrogen bond. So we can identify that as a carbon-hydrogen bond, all right. A little bit less helpful because carbon-hydrogen bonds are in all organic compounds, all right. So it's the first one that identifies it as an alcohol, that shape and where the peak is on the wave number chart. Okay, so in an alcohol there is also a carbon-oxygen bond, all right. So there's also a carbon-oxygen bond. So let's find that here and go the other way. So the carbon-oxygen bond of an alcohol, so the is there between 1,000 and 300, right? So that's in this sort of region here, all right. But because it's in the fingerprint region, right, we tend to ignore that because it gets confused with all sorts of other molecules. All right. So there's the main thing, just to recap, there's the main thing, all right, that the main identifying factor, let's call it, factor for want of a better word, the main identifying factor for the alcohol is this peak here, right, but also the absence of a peak about here, which is a carbonyl group, which we'll see in a minute, which would be present in a hydroxyl group of a carboxylic acid. Okay, so there's a look at the alcohol spectrum and how to identify it. Let's move on to another functional group. Okay, so this is a spectrum of a carbonyl compound, and let's have a look at it as well, along with the data table. So starting off with, let's say this peak here. All right, so looking down, it's sort of just less than 3,000, right, and we can see that. Let's use a different color. We can see that it's all the carbon-hydrogen bonds again. All right, so these ones here are the carbon-hydrogen bonds, like we had in the previous one, and so because carbon-hydrogen bonds are in pretty much all organic molecules, then it's not much help to us. Whereas the next one is, all right, so if we look at this very sharp peak, all right, this very sharp peak, it's about 1,700 here. We look at our table, and we see that that peak is our carbon double bond oxygen. That's our carbonyl group. All right, so this is our carbon double bond oxygen, and we don't have the peak. Remember in the previous chart we had that sort of broad peak about there for a hydroxyl group. All right, so we know it's not an acid, all right, but we've still got a carbonyl group, so that's suggesting that we've got a aldehyde or a ketone here. All right, so aldehyde, looking back at the data table, aldehyde ketone can't be a carboxylic acid because we don't have that peak, and we can't really say anything about the ester, so theoretically it could be an ester. It'd just be a nasty exam question if it was an ester. Because if we looked at the fingerprint region, we'd have to find the carbon-oxygen bond of the ester in there somewhere. All right? And as you can see, it's pretty messy. All right. So if you get a chart like this, your instinct is that it's an aldehyde or a ketone. And to distinguish between aldehyde and ketone, you'd need some supplementary data. Moving on now to the infrared spectrum of a carboxylic acid, that's what we have here. And again, let's have a look at the data table as well. So working from left to right as we look at it, our first peak, let's sort of look at this peak here. Right, so you can see it's about 3,000, and you can see it's very broad. All right, so it's looking at the number first. It could be either of these theoretically, right? But you can see compared to the alcohol hydroxyl group, it's shifted to the right, lower wave numbers, right? So we're going to make out that it's this bond that is making that peak, all right? It's the oxygen-hydrogen bond in a hydroxyl group of a carboxylic acid, all right? So points to remember, it's slightly lower wavelength than the oxygen-hydrogen bond of a alcohol, although there is some overlap there, but the shape is broader than the hydroxyl group of an alcohol. Okay, so we're looking for a slightly broader shape to distinguish it and a slightly lower wave number. Just for completeness, we'll do our carbon-hydrogen bond again, but that's less important. The other important part of this spectrum is this nice, sharp, distinguishable peak here. Right, so the wave number is about 1700. All right, so we look at 1700, and we clearly see it's smack bang in the middle of the carbonyl group again, and so we've got both a carbonyl group, and the green one was our oxygen hydrogen, right? So from those two bits of information, we are hypothesizing that this is the carboxylic acid. Lastly, let's have a look at a spectrum of an alkene, which is the fourth spectrum you need to be quite familiar with. Again, we'll have showing up the data table there so that we can identify each of the peaks. And this one we've met 3 times already. This is our carbon-hydrogen bonds, less helpful. But the way that we distinguish a alkene is this peak here. So it's very fine, and it's at 1600. All right, it's at 1600. So let's pick it out on the data table. We've got this one here is what we see, 1600, slightly more than 1600. So that's how we distinguish this one from this one is an alkene. The sharp peak at 16, just slightly over 1600. The thing to be careful with on this one is not to assume that it's a carbonyl group. So the carbonyl group is slightly less fine of a peak, and it's shifted over to the left there compared to the this carbon double bond peak. All right, so this peak here that we've just drawn here is our carbon double bond carbon, and identifies it as an alkene. And again, we tend to sort of ignore this fingerprint region. Okay, they are the four types of spectrum that you most commonly come across. So let's have a look at them all together so that you can just compare them. Okay, here we have all four of them put together. So let's look at them one by one, starting top left. So this is the acid, this is the carboxylic acid, and how do we know that? Because this peak here is broad, that's broad, and it's about 3,100. But as well as that, we've got at 1,700, we've got the carbonyl, right? So we've got a carbonyl here, and we've got an hydroxyl group of acid there, and that's what tells us that this is a carboxylic acid. All right, moving on to the right here, we're going to have this is our main one here at 1,600. All right, so it's about 1,600. So this is our carbon-carbon double bond. This is our carbon-carbon double bond. All right, so this is our alkene. All right, don't be confused by this one. This is just our carbon-hydrogen peaks. Very distinctive, but it doesn't really help us much, given that carbon-hydrogen bonds are in every molecule. Okay, so we can say that that is our alkene. All right, and then moving bottom left, again, this is our carbon-hydrogen, right? So we don't want to worry too much about that, but we've got a very distinctive peak here at about 1,700, right? So this is our carbonyl group, but we don't have any sort of peak there, so it's just an aldehyde or a ketone. And going to the bottom right, then this is our distinctive peak here at about 3,300, right? And it's broad, but it's slightly less broad than in the acid, right? So this is the oxygen-hydrogen bond in an alcohol, all right? And this is confirmed by the fact that here's our 1,700, so we've got no peak there for our carbonyl group, and don't be confused by this peak here, because here it's 1,500, so it's not a carbon-carbon double bond there. All right, the carbon-carbon double bond would be at 1,600 like it was above. Okay, so this is the alcohol. Okay, so now you see them together, hopefully you can recognize them and identify them.